So today I will talk within the course on mathematical methods for signal processing, on the Shannon Sampling Theorem, and later on about Gabor expansions of signals or so. So I've start with the classical approach to the Shannon Sampling Theorem, which in a way is based on the fact that you're saying, well, band-limited functions are essentially compactly supported functions on the Fourier transform side. So if you're thinking of bandwidth equal to 1, it means you have a symmetric interval of length 1 on the Fourier transform side. And then you would expect, if you translate the standard literature into the current setting, that a function in L2 where the Fourier transform is strictly limited to that interval -1/2 to +1/2, that you can expect that to recover it from a sampling sequence, which is also the integers, and of course you can shift it. So it's an integer lattice or a Nyquist rate of 1. This is again the advantage of having the 2 pi in the exponent for the Fourier transform. Now, the Shannon Sampling Theorem in a way can be viewed as something quite simple. You're having the Hilbert space of all square summable functions only on the interval with 0 outside, so to say, and you verify that the pure frequencies, the integer frequencies, they form an orthonormal system. So you take the exponential functions e to the 2 pi I k times t, and k is running through the integers, and you verify quite easily that they are all an orthonormal system, and that they are a complete orthonormal system, so that every continuous function, and then by combining the density of continuous function in L2, every L2 function can be approximated by linear combinations of these pure frequencies. So it's every periodic L2 function is a limit in the sense of the L2 norm, so if in the square mean, of functions which are called trigonometric polynomials. So it's essentially the story, somebody is inventing a nice orthonormal system, and then everybody knows how to expand it. The only interesting part is that you have to verify that in this abstract setting, the Fourier coefficients, which are just the scalar products between your f and your pure frequency, the coefficients that you put with the pure frequencies, that they are exactly the Fourier coefficients of the function on the Fourier transform side. So it turns out to be exactly the sampling values of the original function. So the Nyquist criterion more or less says, if somebody is giving you a nice band-limited function, and if the sampling rate is good enough compared to the size of the spectrum, mostly described by the maximal frequency, but by frequency shift you can move everything in a symmetric way around the 0, then you can recover. Now, in the multidimensional case, there is a more general situation, because we have not just alpha set d as lattice, and therefore the description I'm giving now is in the general setting, but the proof I will give in the classical setting. So assume somebody has information that the functions that are given through their samples are bounded, confined, the frequencies that are appearing in the Fourier transform, or that are used for the Fourier synthesis part, are to describe a bounded set. Here you can think of a square, a rectangle, it may be even some more fancy thing. And in reality, even, for example, in tomography, something like conic objects appear. Now, this subject should have, has to be paired with a lattice. So what we will need is a lattice, that's where we do the sampling of the functions, and the orthogonal lattice. Now, in order to make it not too complicated, just think of the lattice as a times the integer lattice, and then the orthogonal lattice is 1 over a times the integer lattice. The general principle is, if you do take a coarse set group, lambda perp, then you will have a very fine lattice to take because the volume of lambda multiplied with the volume of the fundamental domain of lambda perp is always constant. So what you have to choose is some lattice, which just by the traditional has to be the orthogonal lattice of some other lattice, such that if you translate your set omega along the lattice, then you don't have intersections, except, of course, if you put lambda to identify the zero element. So 0 plus omega should be different from lambda perp plus omega for every lambda perp different from 0. So we have seen such a picture before. I will not scroll too much now. And the claim is that in this condition, so if you have a sufficiently coarse lattice lambda perp, then you can recover every function from this from the samples on the original lattice from the points. Now, to make sure, what does it mean, a band-limited function? You have the bounded set, and you write that f can be written as a forward Fourier transform, the synthesis with a plus here, of some L2 function h, and of course you first do it for L1 functions. Well, actually, an L2 function on the compact domain is always integrable, so this is, in the sense of Lebesgue, it would be okay. We will later describe it as if the support of the Fourier transform of f hat is contained in omega, but we have no general notion of support yet, so that's why I describe it in this way. And the claim is it can be completely recovered from the sampling values of the other lattice lambda. And you recall lambda and lambda perp are paired in a nice way. And the rule is take your sinc omega function. And what is the sinc omega function? This is just the inverse Fourier transform. It should be inverse Fourier transform, not FFT, of the indicator function of omega. So that's the most general recipe in a Hilbert space setting. We'll see something different, but that's not so important. So somehow it's, you have the pure frequency on the set omega, and if you pull everything back over to the time side, then you will get shifted versions of what is the analog of the sinc function. Now, I will just describe the one-dimensional case, but for the case that you have a unit cube centered at the origin, so it's a pointwise product of intervals of the size -1/2 plus 1/2, then of course the corresponding sinc omega function is again a product of these individual sinc functions. So yes, it's not well decaying, but it's a decent, continuous, and rather smooth function. And as I mentioned, if you want to have a lattice lambda, then the orthogonal lattice will be set D, so sorry, set D is self-orthogonal. That means for the standard set omega, the lattice lambda will be just the integer lattice. That will make things quite easy. And of course, if you have the sampling theorem, for example, for this case, you can do it for other cases by dilation argument. And we know already that stretching the function will compress the Fourier transform and vice versa. So let me go through the kind of Hilbert space proof, which would fit our knowledge, so to say. So I have tried to put things together in such a way that I can say, well, we didn't use Lebesgue integration theory, but of course we expect that the Shannon Sampling Theorem is true for the one-dimensional case. So let's try to prove it now in the classical setting, but in the L2 setting. So the point is we're using the ideal filter. That means we really allow to take any L2 function with a spectrum in the interval -1/2 plus 1/2, and we cut off in a sharp way. And we are aware of the fact that the sinc function is not nice. So the ideal filter is not ideal from the point of view of real-time signal processing because it has so long tails, but that's a different story. Okay, so first observation, sinc convolved with sinc is the sinc function. Now here to the left, we have the convolution of two L2 functions. And that means we can do this in the ordinary way. normally we would get a continuous function vanishing at infinity, but if by Plancherel we can verify the corresponding equation on the Fourier transform side, and that's clearly the pointwise product of indicator functions is harmless. So because 390 is available in a simple pointwise manner, we can be sure that this well-defined equation is also valid. Now, we also have that if you have the support condition on the Fourier transform side, that you can multiply phi f hat in this band-limited function with the indicator function without changing it. And therefore, pulling back, it means f can be reproduced by convolution with the sinc function. This is a quite valuable statement, and in an abstract setting, you would say the point evaluation applying the delta at x to the function f is the same as convolving the function with the sinc function. Now, maybe you observe that the sinc function is symmetric, and therefore you can choose x minus y or y minus x. They're the same thing. But this is an element of reproducing kernel Hilbert space, but we don't need it at the moment. Now, by the Cauchy-Schwarz theorem, or inequality, sorry, we have the pointwise inequality written in this way, allows us to estimate the absolute value of a function which is band limited by a product of L2 norms. So this is a fixed constant for the given set omega. So the good thing and interesting thing is for band limited functions for fixed omega, we can control the sup norm of a function by the L2 norm. So if we're able to verify that we have L2 convergence, we will also get for free uniform convergence. So I think, yeah, we get the continuity, of course, because we have continuous shift of the sinc function in the L2 sense. I don't have to go through this. Now, the main part of the proof will try to imitate the classical spirit, and we would like to look at the pure frequencies on our set omega. Okay, the pure frequency are called chi k here, restricted to the interval -1/2 to 1/2 is this, but we would like to look at them on the time side. So we have to take the Fourier transform of this pointwise product. But the convolution theorem, or the inverse of the convolution theorem in the Plancherel context, we're having only L2 functions and maybe some bounded continuous function, but they are elements of S0 prime if you want. So we can pull it back by pulling back each factor. This is the sinc function, again, because the sinc and this boxcar function are even. And the inverse Fourier transform is just a delta. And so you have the inverse Fourier transform of a pure frequency on the interval is just a convolution of sinc with delta minus k, which is a shifted version of the sinc function. On the other hand, if we call the Fourier transform of f phi, then we have phi hat. And you see the inverse Fourier transform in the forward give a minus, but it fits properly. It's just the scalar product of f with chi k. That's just a definition of what the Fourier transform is. Now this is a decent function, and therefore everything is fine. But then we use, again, Plancherel. So we take the same on the inverse Fourier transform side, which is the inverse Fourier transform phi, but that, of course, is f. And then this guy here turns out to be the sinc function, but the sinc function applied to this in the scalar product, as we have the convolution relationship, is just f of minus k. So the orthogonal expansion, okay, yeah. So the orthogonal expansion is just giving you, take the coefficients in the orthonormal basis and you get the sampling values at minus k, and then the building block is t minus k of sinc. Well, I have to add, there was a question about the Q. The Q should be the omega, so that's a typo, and I will have to correct it. So it's the F hat is a Fourier transform of an L2 function. So it's living on the set omega and 0 outside. But of course, we could also restrict it to the set. So maybe that's a bit ambiguous, sloppy denotation. Okay, so if we say that, and that's kind of the orthogonal expansion on the Fourier transform side, this function phi is characterized by taking the Fourier coefficients times the pure frequencies. We can get the explanation of f, pulling back everything, and we get it's a summation of the coefficients, which are the sampling values, times the inverse Fourier transform of this indicator function, and that's just this summation. And you see you use all the sampling points, and if you replace the summation by k by a summation over minus k, which really doesn't change anything, you get the corresponding statement. So this is the Shannon Sampling Theorem in the, I would say in brackets, non-practical version of the L2 setting. So it's easy in a way. Now, I would like to tell you first that this can be done also in the 0 setting with the approach that we have taken, and here is the corresponding theorem. Sorry. So we have the same situation and some lattice which is fine enough to ensure that the lambda perp translates of the omega set are pairwise disjoint. Then we can recover every function which has its spectrum, as we will say later, or the support of the Fourier transform in omega by such a simple version. Now, the difference to the previous thing is we are a bit we have a situation which is a bit different. The Fourier transforms that we discuss, every function in L1 which has a Fourier transform in with compact support, will be actually a function where the Fourier transform, now we look at this, the Fourier transform is in the Fourier algebra, but it has compact support. And that of course means that we are inside S0 on the Fourier transform side, but because the Fourier transform leaves a 0 invariant, the f is in the space S0. So we're not having L2 anymore completely, but we have decent functions. Now, if a decent function is vanishing outside of an interval or outside of a compact set, it has to go to 0 at the boundaries. So we cannot allow functions to be cut off sharply anymore. That's a kind of a small restriction, but the advantage will be that we have a much better convergence here. And actually, I remember looking up a book of Schüssler and co-author where they are doing exactly this in order to improve the locality in the case of the Shannon Sampling Theorem. The price is a little bit of oversampling. So the lattice may have to be like 10% better than the critical lattice, but you get locality. Just think of modern digital devices like the CD player. The idea is to capture frequencies up to 20 kilohertz. Now 20 kilohertz would require a sampling rate of 2 times 20 kilohertz, which is 40,000 samples. But in reality, we are taking, or the convention has become to take 44,100 samples, which is on the one hand a very nice natural number. I always say it's 2 times 3 times 5 times 7 squared. So you have a lot of different divisors. You have a fast FFT if you take chunks of a 1 second or fraction of 1 second. And you have like 10% more than the minimal rate, which is would be 40,000. But you can do things much better in real time. You would not like to wait for 2 minutes or maybe even a full second until you start processing, but you would ask to get a few samples, like a few microseconds, so that you have still the idea that you don't realize, I mean, your senses don't realize the minimal delay, because it's not real time in the strict sense, but it's real time in the practical sense only. Okay, so what is the claim? We can recover, and what you see here is the same form of lattice, a little bit more dense than the classical Nyquist criterion, but the G here can be chosen to be relatively general. What we need is that the G, and I'm starting with a 0, therefore I want to rebuild everything in a 0, so all these building blocks should be in a 0, and that's what we do. So we take a function which is in a 0 and which has a Fourier transform which has the same property as the boxcar function, so it reproduces the inner part. On the set omega it should be 1, but it should suppress all the other copies. So it should be disjoint, so the intersection I should write, this should be the empty set for any shifted version. So if you imagine that lambda is a little bit more dense, then of course lambda perp is a little bit more sparse or wide, and then there's enough space between the omega and the lambda perp translates of omega, and so it's quite easy to fabricate such functions. For example, you're taking a boxcar function which is a little bit larger, and then you smooth it without destroying the property of the plateau in the inside or so. This is actually what in the book of Schüssler has been described. Also, in all practical cases, you will choose a function which is just L1 and where the Fourier transform of G hat is compactly supported. So you just use the free space between the set omega and the copies to go down to 0 in a smooth way, because smoothness of a function corresponds to good decay. Just remember the convolution powers of the boxcar functions, which is just the original one is the sinc function, poor decay. Triangular function, already sinc square, already integrable. Cubic polynomials going Fourier transform going down like sinc to the power 4, which is like 1 over x to the power 4. Very nice, decent decay. Okay, so let's forget about the Hilbert space stuff. Let's do something more practical using our information. Any band-limited function in L1 belongs to a 0. This was the first statement. And in fact, we even have the following estimate, which I was putting in the script at some place meanwhile, that you can control the S0 norm by constant times the L1 norm. So for a fixed set omega, you can either use the L1 norm for the band-limited functions or the S0 norm. So according to the assumptions, we have such a function. And therefore, again, if you give me any lattice, I can estimate the L1 norm of the samples by some constant. And actually, I should better write here constant omega depending on omega and lambda, because if somebody is sampling very densely, then of course you get a bigger sum. So just think of, take the integer lattice and you get the sum, and then take the half integer lattice, you get about twice the sum. So if you would normalize by the size of the fundamental domain, then you can have a uniform estimate which does not depend on the lattice, or at the moment we're just saying, just take a constant which depends on the size of the omega and on the sampling lattice. Of course, a big set omega means that you might have a large constant. Now, the task is to reconstruct from the samples. And now we use the simple fact that multiplying a continuous function with a Dirac delta is just f of the value times the delta. So here you sum up over all these values. And if you discuss it in a pedantic way, you have to say, well, the Dirac comp, the sum over the deltas, is the weak star limit of the finite partial sums, which simply says if you applying this to a function in S0, and if you take more and more of these lambdas, points lambda, then it will converge. Well, we also know, meanwhile, by this condition, it's absolutely summable. So we have a description of a finite, bounded discrete measure sitting on the lattice, and it's obtained by this pointwise multiplication. The main point of my story here is lambda is a lattice, and SHA lambda, or the Dirac comp at lambda, is a well-defined object. We are allowed to multiply this element from the dual space, so I call it a mild distribution, with a function from f in S0. And it's having this concrete form. And we are having everything Fourier invariant. So the Fourier invariants just say, well, up to a constant, and that's forgotten above here. We have the Poisson formula in the general format. We have the SHA distribution at the orthogonal lattice, and then you convolve it with the Fourier transform of f hat. But this is a well-defined periodic function. So we are taking the f hat, we are periodizing it along the lattice lambda perp. And so what we need is just to say, well, this is a bunch of copies, and they are quite well separated. So what we do is we multiply it back to get the f hat from these copies, and then we say, this is the Fourier version of what we want to have. And so clearly we say, well, how can we get back f from f hat? We have to apply the inverse Fourier transform. Of course, we apply it to the left-hand side of what we have written here. But this is a pointwise product, and of course, f to the minus f inverse Fourier transform of g hat is the g. Now I'm writing on the right-hand side, but this is no problem. And then we're saying what we get back is, of course, what was our starting point, the sampled version of the Dirac. But now we read it slightly different. We're saying, and this is of course justified because everything is absolutely convergent, this is an infinite sum, but nicely convergent, of amplitudes, which are called f lambda, times bracket now delta lambda convolved with g. But that's just a shifted version of g. So we have absolute convergence in S0, which of course means we have convergence in L1, uniform convergence, and in LP norm, and so on. So there is absolutely no problem. So you see, I think it's worthwhile to remember this version of the sampling theorem, because it's a practical version, and it just boils down to what we have seen more or less in the MATLAB experiment, or what you can easily demonstrate. Sampling, that's what happens here. Sampling on the time side corresponds to periodization on the frequency side. If you're able to undo it by localization, by cutting out one of these repeating elements on the Fourier transform side, we are able to recover the function f. Now, I think it's a good idea, and that's one of the side effects or side purposes of my presentation here, is that I would like to show that what I can demonstrate with MATLAB is something that with the setting of mild distributions is quite well realizable. So in the MATLAB setting, I would say, well, we have this decent complex valued periodic function. So think of this graph being wrapped up on a cylinder, and that has a spectrum. Actually, that's how I create such a low pass signal, by taking random complex numbers. So I'm actually showing you here a complex trigonometric polynomial, and that has a Fourier transform. Yeah, I have okay, so here is the Fourier transform side. Now on the time side, we're doing a sampling. And you can imagine that I'm sampling at a rate of 10, which means that I'm getting 10 copies of this very narrow band signal or so. And then this multiplication with a rectangular function, so that would be in my case a boxcar function, which is symmetric. If it's in MATLAB, I would say I have to put 10 ones to the right of my 0, so I have 11 ones at the beginning of this discrete sequence and 10 at the end. That would be corresponding to a symmetric filter here, and I would cut out. Now, if I do the same thing, and that's now or maybe already part of the explanation, the set omega is the support. It's the area where the function is living in the one-dimensional setting. But now I'm choosing a red guy, and this red guy is trying to recover from the samples in the same way. I think in the I'm not sure, but I think in the previous, if I look at the example, probably, yeah, okay, it's a different signal, but maybe I'm choosing here, I was doing this at another time, so I'm choosing another random, maybe with a slightly more narrow bandwidth, but I'm using a red function now on the Fourier transform side. So this is my G hat. And of course, I'm constructing in such a way that I have constant 1 in this area where I reproduce, and the other are disjoint, and there is some space in between. Actually, I don't have the space to be inside. I mean, the support has not can be larger. It can touch more or less the neighbors, but there is a free space. So it's kind of the amount of oversampling, so how much more density I have on this side corresponds to the room that we have here. So in the most simple case, I would just take a trapezoidal function here that would already allow me to make a plateau here and then linear going down. Okay, now I'm not sure, I have to see, but probably it's not worthwhile. Okay, yeah. This is another picture that tells you why you can expect that the more smoothed version of the plateau function is really much better. I mean, probably this is not a complete fair comparison, because here the rectangle is a little bit too narrow, but I could make it a little bit wider, and still you would have all these wiggles and the tails. I mean, we are in the periodic setting, so it's not perfectly the continuous setting, but clearly this guy is much better concentrated than this guy here. And it's clear because if you want to have certain Fourier coefficients in a discrete setting which give a jump function, then you need high frequencies. You cannot build with only low frequencies a function which is having a jump, and therefore you have expect that the smoothness here corresponds to good locality and vice versa, which is actually the case. I'm not sure. Yeah. Now, the problem with LaTeX is that the plots are spread out, whereas in the script they are closer together. I mean, in the LaTeX code they are closer together. So what is the advantage of having building blocks which are coming from a G as we had it in the 0 setting, while all these building blocks are much closer? So what I was doing here, the experiment, is that I'm just saying, well, we get our function back, and here, of course, I was choosing a real valued version. So I take a band limited function and either concentrate on the real part, or I just make it real valued first. And then, yeah, well, maybe just to mention, what does it mean to go to the real part? I mean, you add, you take 1/2 of the original function plus 1/2 of the conjugate. Now, the conjugate of a function is just the flipped version on the Fourier transform side. So conjugation goes to f flipped conjugate. So this is the f star. Now, if your original function is band limited in some symmetric set omega, then of course the support of the flipped version or this conjugate is in minus omega, but by symmetry that's the same as omega. So I can produce, just by taking the real part of a band limited function for a symmetric bandwidth interval, I can be sure it's also band limited in the same way. So the same reconstruction works. We take a function, of course, which is real valued and symmetric if possible, as I was showing you my red guy, and then it means that the inverse Fourier transform is also symmetric and even. So these building blocks in the S0 version of the Shannon Sampling Theorem are these nicely colored guys, the red, brown, and so on. and each of them taken at the right position where we had the sampling. So you can imagine how this thing looks like. And now I'm not sure, I was doing another explanation to say, well, in reality, we don't have all the samples. I mean, the theorem says we have nice convergence of this infinite sum, meaning infinitely many sampling points. And in the L2 setting with the tails, if you're really doing many samples, everything is fine. But assume somebody is only giving you finitely many samples in some region. So here, of course, it looks like I was taking the samples between, I don't know, 120 and 360 or something like this. So I'm choosing some interval, and that's, I think, very realistic. You have some band-limited function, and you're sampling it in a certain region. Actually, we had once a cooperation with people from geophysics, and they had geophysical measurements of gravitational potentials. And of course, what they were doing is they were measuring along a grid, but the grid was not perfect. So they were saying, okay, we know exactly where we have taken these measurements. Now, by the laws of physics, gravitational potentials are very smooth functions, so it's very plausible to approximate them by band-limited functions. And we were trying to apply our irregular sampling algorithms, which is a version of the Shannon Sampling Theorem, but requiring iteration. And then, of course, I mean, you know that at the boundaries of your domain, you have some errors, but you would not like to have big spoiling effects or requiring to cover a huge domain with many sampling points just to have a reliable reconstruction in the inside. So it's a very good practical point to know what kind of reconstructions can you do. And the story that I have tried to explain today at this course is that if you're doing a little bit of oversampling and make use of the oversampling by replacing the boxcar function, the so-called ideal filter, by a smooth version of it, but keeping the reproducing property in the center and the kind of avoiding the copies, then we have a reconstruction. And here, of course, for demonstration, I was trying to zoom in to make it quite reliable. Here you don't see a big difference. So the difference is between the function and the reconstructed function. Whereas if you would sync functions, then the missing samples, which we didn't have available, put into this ideal formula give an error even in the area, as I mean, a visible error in the range where we had this sampling values. Okay, I'm not sure if there is one more thing. No, I think this is, yeah, maybe something like this. No, that will be used in the next part. So from my point of view, I think it's a good point to stop here. And I will continue with the second part of today's session with explanations concerning Gabor expansions.